Another example where differential equations get used is in the field of chemistry. What we're going to think about here is rates of reaction. So chemists like to think of, for example, reactions. You might have some chemical quantity or species A, which is turning into two other species B and C. For example, that would be a chemical reaction. And this would give you what's called a first-order chemical reaction, where the rate of change of the concentration of A, and chemists use the symbol A in square brackets to denote the concentration of A. So the rate of this reaction, which tells you the rate of change of the concentration of A, is just proportional to the amount of A. So A is going to be decreasing with time because A is turning into B plus C. So again, we need a minus sign and a K, which is the proportionality constant. And then it's going to be proportional to A. Well, you recognise this equation already. This looks just like the radioactive decay equation that we had in physics. So this is what's called a first-order reaction. But sometimes chemical reactions are not so simple as A decaying into two species B and C. Perhaps you have another chemical reaction which is A plus another species B, which is going to give you some product C. And for this reaction to occur, you need your chemical species A to meet your chemical species B. And so the rate of this reaction, which still gives you the rate of change of the concentration of A, is actually proportional to the concentration of A times or multiplied by the concentration of B. So that would give us minus K times the concentration of A and the concentration of B. And then you need to think about what your initial concentrations of A and B and relate your concentration of B to your concentration of A, and so on and so forth. But this is called a second order reaction. And again, both of these are differential equations, and solving those differential equations tells you how much stuff you get out of your chemical reaction as a function of time. The final example I was going to give is in the field of ecology or sociology or biology, basically anywhere where you're interested in population dynamics. And in population dynamics, often you find that the rate of increase of whatever is in your population, it could be people, let's call that P, it could be bacteria, let's call that B, it could be rabbits, let's call that R, whatever, then the rate of increase of these things is proportional to the number of whatever it is you have, people, bacteria, rabbits. So the equation you'd write down here is, for example, if we were talking about rabbits, dr by dt, the rate of change of the number of rabbits, is equal to, and it's an increase now, so it's a plus sign. It's proportional to the number of rabbits. Again, there's a proportionality constant, and that would be the equation we'd write down. Well, this looks very similar again to the radioactive decay equation, but instead of a minus sign here, we have a plus sign. So the solution to this equation actually is R, the number of rabbits, is equal to the initial number of rabbits times e to the kt. And so the number of rabbits as a function of time starts off at R0, but then increases in what's called an exponential fashion. Now, according to this equation, the number of rabbits should increase and increase and increase off up to infinity. That's a lot of rabbits. So there must be something, actually, which stops the number of rabbits from growing. It could be foxes, or it could be just lack of food. So you might want to put some corrections to this equation to deal with the fact that the number of rabbits can't grow all the way off up to infinity. And actually, we'll talk about one way that that's done in a minute or two. So already, actually, as I've been talking through these different examples, you'll have seen the way I think in terms of trying to formulate different kinds of differential equations. So if I was going to give some tips as to the sort of things you might think about when you're trying to formulate a differential equation, there's three things I would say. The first thing I would say is you need to think about whether the quantity you're describing is increasing or decreasing. So what does that mean? That means if you've got some quantity, let's call it x, which is changing with time. If it's an increasing function, you would have a plus sign. If it's a decreasing function, you would have a minus sign. The thing on the right needs to be positive if it's an increasing quantity. It needs to be negative if it's a decreasing quantity. The second thing I would say is if you can see in the words the word proportional. So if something is proportional to something else, you will need to introduce a proportionality constant. So that might be this constant k. You can invent your own letter usually for these things. On the other hand, if the question says, or the model says that the rate of change is equal to something, then you don't have the proportionality constant. And the last thing I would say is look for word clues. Look for clues like product or ratio or sum or that sort of thing. These are words you will spot in the question or in the model that you're trying to formulate. Those tell you what goes in here. Is it the product of two quantities? Is it the sum of two quantities? Is it the ratio of two quantities? If you can look for those clues, that will help you very much in answering these kind of questions. Okay, so I'm going to give you a couple of very quick examples as to formulating differential equations. These are based roughly around some of the examples that I've seen in various exam papers. So the first example is this, and the question says, let n be the number of bacteria, measured in units of 100,000, in a culture on a dish. Because of the size of a dish, a biologist thinks that the population can't increase above 1 million. So she proposes that the rate of increase of the population of bacteria is proportional to the product of n and n max minus n, where n max is the maximum possible value of n. And we're asked to write a differential equation for this. So what do we have? We have a load of bacteria on a dish, and the number of bacteria is actually n times 100,000. And we're also told that the maximum number of bacteria is 1 million, so you should be able to work out quite quickly that n max, the value of n when we reach the maximum number of bacteria, must just be equal to 10. Because when n is equal to 10, then the number of bacteria, actually I've made a mistake, bacteria, there we go. The number of bacteria is just n times 100,000, and so when n max is equal to 10, then the total number of bacteria is 1 million. Okay, now we get to trying to write down a differential equation for this. And you should be able to spot some of those words I was talking about. So the first thing it says is the rate of increase of the population of the bacteria is something. So we should have dn by dt. It's an increasing quantity, so it needs to be a plus sign. The second thing is it says it's proportional to something. So we need to introduce a proportionality constant. And then it says it's proportional to the product of n and n max minus n. So if it's proportional to a product, that means one thing multiplied by another thing. So it's proportional to the product of n and n max minus n. Well, n max is 10, so that's 10 minus n. And that's it. Simple as that. That's the differential equation which works for the model that this biologist has proposed. And in a few minutes I'll say something about how you might go about solving that kind of differential equation. The second example I've got is this. Now let's suppose we've got some vat, here it is, and you've got some level of water in that vat. Why don't we very quickly colour that in blue just for the fun of it. There we go. We have some water in that vat. And there's a height h of the water in the vat, and the vat is 1 metre length in that direction, 2 metres length in that direction, and water is being poured in here at a rate of 4 metres cubed per hour. But because there's some tap or other, the water is coming out at this side at a different rate of 6 times h metres cubed per hour. So we might want to write a differential equation for the rate of change of height of water in this vat as a function of time. Okay, so how do we go about doing that? Well, the first thing to think about is, well, what's the volume of water in that vat? The volume of water, let's call that V, is equal to H times the area A of the base. And the area A of the base is just 2 meters squared. So we can say that the rate of change of volume is just equal to the rate of change of height with respect to t times A, or I can turn that equation round and say, well, and I'll just delete this up here, dH by dt, which is the thing we're interested in, is equal to the rate of change of volume with respect to time divided by the area A. And we told something in the question about how this volume is changing with time. We've got a positive contribution to the volume change from the water going in at the top. We've got a negative contribution to the volume of water from what's escaping down at the bottom. So we've got everything we need to put into this equation. So we have dH by dt is equal to the different contributions to dV by dt divided by the area, and the area is 2 meters squared. So we've got a positive contribution to dV by dt from the water coming in at the top, and that's just 4 meters cubed per hour. And you can see I'm working in units where the lengths are meters and the time units are hours. And we've got a negative contribution to the rate of change of volume, so that's going to give us a minus sign, and then we've got 6h meters cubed per hour escaping out to the bottom. So all that's required now is actually just to tidy this up. So dH by dt is equal to 2 minus 3h. And again, this is the differential equation which governs the rate of change of height of that water in that vat as a function of time.